Section 7.4, Basic Trig Equations. So basic trig equations have one of these three forms. So it's going to be sine, cosine, or tangent of theta equal to some constant. And then the goal is to solve for theta, all possible values for theta that make the equation true. Okay, so the steps for solving a basic trig equation are always the same. You're going to first find, in step one, all solutions in one period of the trig function. And then in step two, in a pretty automated way, you'll write down all of the solutions to the equation then. Okay, so we'll do an example of each type, the sine, the cosine, and the tangent. So here's a basic trig equation involving sine, trying to solve sine theta equal 1/2. Again, what that means is we're trying to find all values of theta that make the equation true. Okay, so following the outline, step one, we need to find all solutions in one period, and we mean one period of the sine function. Okay, so the sine function has period 2 pi, so it's probably most natural to find the solutions in the interval from say 0 to 2 pi. You could also go from minus pi to pi, or if you really wanted to freak someone out, you could say, I'm going to look from pi to 3 pi, but 0 to 2 pi is usually where we look. And to do this, it's most helpful to think about the unit circle. So for the unit circle, remember the sine is the y-coordinate of a point on the unit circle. So we're looking for points on the unit circle that have the y-coordinate equal to 1/2. And there are two such angles, the pi over 6 angle and the 5 pi over 6 angle. So those are the two values of theta in the interval from 0 to 2 pi. There are no others where the sine is equal to 1/2. So that's what we write down first. We have the pi over 6 and the 5 pi over 6. 5 pi over 6. Okay, and now step two, we want to give all solutions, and we do that by adding on multiples of the period for sine. Okay, so one of the solutions was pi over 6. We'll get other solutions when we add on any multiple of 2 pi. 2 pi, a 4 pi, 6 pi, and also negative multiples like minus 2 pi, minus 4 pi, and so on. And we also get that when we add 2 pi, multiples of 2 pi onto 5 pi over 6. And again, the reason that this happens is that sine has period 2 pi, and that means its values repeat every 2 pi. Okay, so this is a convention for trying to express the solutions. Here's a table of values for specific values of k, just a few values of k. So when the k is 0, we get the original two solutions that we found, the pi over 6 and the 5 pi over 6. When k is 1, well, adding 2 pi, that's the same as adding 12 pi over 6. So pi over 6 plus 12 pi over 6, that's getting us to the 13 pi over 6. Here's adding another 12 pi over 6. And here we're going the opposite directions. When we're subtracting off 2 pi, we get these solutions. This is what we get when we subtract off 4 pi. Right? Again, these are the values of k. Okay, and we also get those additional solutions when we add multiples of 2 pi to 5 pi over 6. Okay, so here's the graphical confirmation of what we're finding here in this table. Is, again, we're looking for the solutions. When does sine of theta equal 1/2? So graphically, we're trying to figure out for what values of theta does the sine function intersect the horizontal line y equals 1/2. And pi over 6 and 5 pi over 6, those were the two values that we found initially. And then when we add a multiple of 2 pi to pi over 6, well, for example, we get to 13 pi over 6. And if we subtract off 2 pi, we get back to negative 11 pi over 6. Right? And adding multiples of 2 pi to 5 pi over 6 is bringing us out to this point, back to this point here. Okay, so there are infinitely many solutions to this equation, and we're graphically seeing 6 of them here. Again, the solutions are the thetas here. So the solutions aren't actually the red dots. The solutions are these values of theta listed in the table. Okay, it's a sine example, a fine sine example, and here's a cosine example. So we're going to solve cosine theta equal negative root 2 over 2. Again, this basic equation, we have a trig function set equal to a constant. And the outline is still the same. We find all solutions in one period. Right? Just like sine, cosine also has a period of 2 pi. And so it's probably most natural to find the solutions in the period that goes from 0 to 2 pi. Again, you could go from minus pi to pi or other intervals, but that's probably the most natural. Okay, going to go into the unit circle. We're looking for, this time, x coordinates that are equal to minus root 2 over 2. So there's supposed to be negative x coordinates, and there are 2 such values for theta. They are 3 pi over 4 and 5 pi over 4. Now, I copied this graphic out of the book, but I just made a note that it does look a little funny to me. These pi over 4s are supposed to be at the 45-degree lines, and they look a little too steep to me. I don't know. I didn't bother trying to correct this, but something looks amiss with that picture. But in any case, from the unit circle, we pick up these 2 solutions in this interval, in the interval that we agreed on, the interval from 0 to 2 pi, representing one period of the cosine function. Right? And now we give all solutions, again, by adding on 2 pi multiples to the 2 solutions we initially found. And again, the reason that we're adding on multiples of 2 pi is because that's the period for cosine. Cosine is going to repeat its values every 2 pi. Right? Same thing as before, we'll look at the solutions in table form. When k is equal to 0, we're getting the initial 2 solutions that we found. When we add on a multiple of 2 pi, for example, when we add on 2 pi, that's the same as adding on 8 pi over 4. So that's how the 3 pi gets to 11 pi over 4. And we can also subtract off multiples of 2 pi to get out the solutions. Right. The graphical confirmation here, this is the cosine function this time, and we want to know when does it equal a negative root 2 over 2. So when does it have outputs equal to negative root 2 over 2? We're seeing this graphically as the intersection of cosine with the line y equals negative root 2 over 2. Again, there are infinitely many solutions, and this is the notation that we use to try to represent those solutions. I think, yeah, I'm sure I'll allow this. On the exam or quiz, it's just understood when you write out this as your answer. It will be understood. I will understand you to mean that k can be any integer. You won't have to write that little phrase at the end. Okay, so that was the sine and the cosine, and then the other basic one is the tangent equation. So tangent of theta equals to some constant. Here we're picking an easy constant, constant 1. Okay, so again, follow the steps. We find all solutions in one period. Well, this time we have to remember that tangent has period pi, not 2 pi. So we're going to look for solutions in the interval from minus pi over 2 to pi over 2. And it would be perfectly reasonable to say, well, why aren't you going from 0 to pi? And the reason that we don't do that is that pi over 2 is not in the domain for the tangent function. Because cosine is equal to 0 at pi over 2, the tangent winds up being undefined there. So this is the most common interval to look for solutions to a tangent equation. Okay, I haven't drawn the picture this time, but if you remember, tangent is sine over cosine. So if we want the tangent to be equal to 1, we're looking for angles where the sine and cosine are equal, and that happens at pi over 4. And that's the only value in this interval. Okay, once we have that, we're going to put in a little blank here for emphasis here. We're going to take the one solution that we found, and we're going to add on multiples of the period for tangent. So we're not going to add on multiples of 2 pi, we're going to add on multiples of pi here. And again, k can be any integer. Okay, so the table, this time the table's only got one, well, it's got 2 rows, one for the k, but only 1 row for the solutions here. So when k is 0, we get that initial solution that we found, pi over 4, and then we get other multiples by adding on multiples of pi this time. Not multiples of 2 pi, but just multiples of pi. It could be positive or negative multiples of pi. Right. Here's the picture when we're plotting out the tangent function. Again, this has period pi. It's repeating every pi units along the horizontal axis. And we're seeing when does the tangent have a value equal to 1 by seeing where it intersects the horizontal line y equals 1. And there are infinitely many solutions to this equation. Okay, well, this is good. I'll put in a timestamp, but I think this will be a quick day. We're at 12 minutes. So those are the basic equations, and then the question is, well, how do we try to solve more complicated equations? Well, what we're going to do is use some algebra skills to convert the more complicated equation into a basic equation. Right? So the first idea is simply trying to isolate the trig function. A basic equation has the trig function all by itself on the left-hand side. So just a couple of examples here. Solve secant theta. Well, secant theta wasn't listed as one of the basics. We said cosine, sine, and tangent. So what we're going to do, I guess this isn't the algebra. The first thing here, this is the trig identity. Secant is 1 over cosine. But now we're going to use the algebra skills. Now we want to isolate that cosine on one side. So we'll multiply both sides by cosine theta, and now we're going to divide both sides by 2. And now we've isolated the cosine by itself. Now this is basic. I mean, we just learned how to do it, but this follows the basic formula. So 1 period, so in the interval 0 to 2 pi solution. So we are looking for where is the cosine equal to 1/2. Again, we're drawing on our unit circle experience. We want the cosine to be positive, but a fairly small value that occurs at pi over 3. Actually, now that I've written this, I think I'm going to change my mind here. I think it would be actually easiest to go on the period from minus pi to pi. So the other solution I would like to include is minus pi over 3. I like to think about the up and down angles as being symmetric and giving me the same cosine value. It wouldn't have been wrong to say 5 pi over 3, and maybe I should have just gone ahead and done that to avoid any complication. But in any case, this is step 1, and then step 2, we add on multiples. So all solutions. Oops, missed my theta. That's pi over 3 plus 2 pi k, because the period for cosine is 2 pi. Minus pi pi over 3 plus 2 pi k. Okay. I don't have enough clear to make this a separate example here. Solve. Okay. So here we have an equation that has one of the basic trig functions in it, a starter, a cosine, and all we need to do is some simple algebra to isolate that cosine on one side of the equation. Okay, so I don't know how many steps, I guess it won't take that many steps. We'll subtract the 4 from both sides and then divide both sides by 2, and this is the equation we just solved. So we won't solve it again, but the point here is to isolate that cosine theta and then solve the resulting basic equation. Okay. So there's another type here. I don't know what to do here. Usually I put oh my gosh. Don't have any idea where that came from. Sorry, I gotta push pause here. Okay, sorry, I don't know what that was in my copy paste menu there that exploded on the screen. It startled me just a little bit, but I think we're back. Okay, so this is close to a basic, except the difference here is that on the left-hand side we have sine squared. So we're going to try to solve for it, and because sine squared is appearing in only one place in this equation, the simplest way to do this is to take the square root of both sides. But when we do, we just have to remember on the right-hand side we need the plus or minus option. So what this leads to is solving two separate equations. Now we're going to have to solve sine of theta equals, well, let me simplify this first. This square root 3 quarters is equal to square root 3 over 2. We can take the square root of 3 and square root of 4 separately. So this leads to two separate equations to solve. One is sine of theta equals minus square root 3 over 2, and the other is sine of theta equals square root 3 over 2. So double the fun. How do we do this? Well, these are now basic equations. So step 1, in the interval from 0 to 2 pi, we're looking for where is the sine equal to minus root 3 over 2, and this takes the unit circle approach again here. We're looking for a big and negative y coordinate. So this is going to be a steep angle in quadrant 3. Oh, what is that going to be? I guess that's I'm having trouble here. It's a pi over 3. It's a 4 pi over 3. Uh-oh. Okay, so it's 4 pi over 3, and the other steep angle, this is 5 pi over 3. And this is just for the first equation. Solving this equation. Those are the two angles in one period, and then so this is going to be quite a list by the time we're done here. We're going to get all the solutions when we add on multiples. I guess really I should be writing or here. It can't be both. So these are the solutions to the first of the two equations, 2 pi k, and for, let's see if we can expedite this with a little copy paste. For the other equation, when we're looking for positive root 3 over 2, well, these are the the steep angles, the pi over 3 angles in quadrants 1 and 2. So those are pi over 3 and 2 pi over 3. Certainly, I mean, having a nicely drawn out unit circle at your side would be a good idea when you take the exam. Okay, so combining this, the final answer, just to be clear, final answer, solutions to the original equation, this one that had the square in it, are all 4 of these possibilities. Ugh, didn't typeset right. Why is this not typesetting correctly? Okay. Or these, where k is any integer. So we get 4 different types of solutions. All right, that was quite a long example. Here's another one. Again, the complicating feature here is the square, and also it's not isolated. So what we want to do is try to isolate the sign. This is sine squared theta. Let's see, we'd subtract 1 from both sides, so 3. Sorry, getting rushed here. That's subtracting 1 from both sides, and then dividing through by 4. And again, we just solved this. So we won't solve it again. That's one that we just solved. One more example here. Certainly not basic, but our goal here is to somehow try to isolate the sign. So one possible technique would be to multiply both sides by, and again, this is just an algebra skill. This isn't really a trig skill at this point. We're just going to multiply both sides by sine theta, and now we'll be isolating by dividing through by the 4. And again, we just solved this one. So sometimes there are a couple of additional steps in advance of getting that square and then taking the square root. Right, so, but these are algebra techniques. All right. Put in a 2230 timestamp here. So this first idea basically was we're trying to isolate the trig function that's in our equation, and the slightly more complicated situation is going to require factoring. Now, factoring is a skill that you learned in algebra, and we're going to bring it to bear here as well. So here we have an equation, and the variable is theta. There's a mix of terms here. We have both a cosine and a sine. It's initially looking just quite crazy, but we're going to fall back on just a reliable strategy for solving equations in general, is to get 0 on one side and then attempt to factor. All right, so I'll subtract cosine over to the left-hand side. And now on the left-hand side, I've got a difference of 2 things, and I see that cosine theta is in both of them, and that's what allows me to factor. So I'm going to factor out a cosine theta, and that leaves behind a 2 sine theta and a minus 1. Okay, so the reason that we factor, once we have something set equal to 0, is now that leads to 2 separate equations. Oops, so cosine theta equals 0 and 2 sine theta minus 1 equals 0. Right? This one's basic already. Yay, it's basic, so we should be able to solve it. This one is not basic, so it's going to take just a little bit more algebra. 2 sine theta equals 1. Add 1 to both sides. And now divide both sides by half. And so now this one is basic as well. Yay! And so we should be able to solve each of those separately. And again, the solutions to the original equation will combine the solutions to both of these equations. maybe I'll try to write them down as quickly as I can here. Solutions to cosine theta equals 0 are, well, in the interval from 0 to 2 pi, there's only one angle where the cosine is 0, and that's the 0 angle. So when I said 0 to 2 pi, maybe I should have written that down. From closed 0 to open 2 pi interval, theta equal 0 is the only solution, and then we add on any multiple of 2 pi to get the other solutions. So I kind of jammed both step 1 and step 2 into a single step there. So here we have pi over 6 as one solution in the interval, and we add on a 2 pi k, or the other one where the sign is a half. Again, this is a unit circle, is 5 pi over 6, and we add 2 pi k to that as well. So these three collections here are representing the solutions to this original equation. Okay. Yeah, always optimistic about finishing quickly, but right. So this is going to require factoring a quadratic. Now, the first factorization that we did not have a quadratic. We had two separate trig functions and just factored out the cosine. But here we've got cosine squared appearing, but also another cosine here. And so we can't just take the square root to isolate the cosine now. If we only had cosine squared appearing one time, we could isolate it and take square roots. But this is actually going to take a factoring. So again, the step is to get 0 on one side. So let me do that with a copy paste. And this is kind of a challenge to factor because the squared term out in front has a coefficient on it. But it is going to factor as 2 cosine theta plus or minus something. Oops. And then cosine theta. And it's, again, we have to figure out what goes into these little boxes here. It's got the boxes have to multiply together to produce minus 1. So let me try a minus 1 here. Oops. Minus 1 here and a plus 1 here, and see if that works. This is probably too much detail here. Okay, sorry about that. The original problem that I was trying to solve had a typo in it. This was supposed to be 2 cosine squared minus cosine. So I subtract a 1 over, and now when I try to factor, I think what I need here is this one to be positive 1 and this one to be a negative 1. And that would equal 0. Let's see if that's right. 2 cosine squared. I get a minus 2 cosine and a plus cosine. Yes, that is correct. Okay, so again, the idea of the factoring is now that we've got a factored quantity, factored expression set equal to 0, we wind up with 2 separate equations that we solve independently. Okay, neither of these is basic, but it's in very short order that we bring them into basic form with just a minimal amount of algebra effort. Yay, basic. And this one becomes basic after just one step. And we solve them separately. Okay, right, so the typo I had in that problem, this was supposed to be just a U, not a minus, it's supposed to be a 1, not a 2. So sometimes when you're trying to solve these quadratics, it's easier if you use a u substitution. So totally optional, but I'm just going to redo the problem that I just did by setting u equal to cosine theta, and then rewriting the equation now. This is 2u squared minus u equals 1. And then try to solve this. It's perhaps, arguably anyway, a little easier to solve this quadratic when you just have a single letter instead of cosine theta, right? So the factorization is going to be 2u plus or minus something and u plus or minus something equals 0. Again, the somethings have to be multiplying together to give minus 1, so the two things to try are minus 1 and plus 1 in one order or the other. And that's the wrong choice, and this is the correct choice. Oops, minus, because I'm getting a positive u and a negative 2u, which combine to give me the negative u that I want, right? Well, so this says that you're going to solve 2u plus 1 equals 0 and u minus 1 equals 0. But now you return to the actual identity for the u. U was 2 cosine theta plus 1 equals 0, and cosine theta was equal to 1. Right, one more example, and then we'll be done. Okay, so again here, this is optional, but I'll do it, optional u substitution of u equals sine squared theta, potentially making the factorization a little easier. So the equation would be u squared equal 2u plus 3, and we say, oh, this is a quadratic. I need to get 0 on one side and factor. So I'll move the 2u and the 3 over, and now I'm trying to factor. This looks like u minus 3 and u plus 1 equals 0. Okay, so that leads to two separate equations to solve. The two separate equations are u minus 3 equals 0 and u plus 1 equals 0. But as soon as we write those down, we substitute back now. We'll be trying to solve sine squared theta equals, minus 3 equals 0. Sorry, I botched that. So I'll make that correction. This substitution that we were using here, we replaced sine with u, not sine squared. Right, so I knew something looked very fishy there. And then this one becomes sine of theta plus 1 equals 0. All right, we'll do this one just one more step here, because I don't think we've seen an example like this. 3, just to point out that this equation, one more, has no solutions. There's no value of theta that has a sine equal to 3. Sine is always some number between minus 1 and 1. And just for the end game here, we solve this one for sine theta. This is a basic now, and we can solve it. Okay, that's it for section 7.4.